so far? Okay, we were on the probability, the law of addition. When you're taking the union, a formula you can use is to add the two together and then subtract their overlap. And the other is a definition. Mutually exclusive means they have nothing in common, and so their intersection is the empty set. When that is the case, then you can just take A union B because the intersection is nothing. If I look at the first one, it says find the probabilities for each. If we want to find the probabilities, since we were able to list all of them, we know the union is 1, 2, 3, 4, 5 out of the 6, or 5, 6. So if you have them all listed and you can see which ones they are, then you just add the probabilities. Intersection is 2 out of the 6. Now, if we were going to use the rule, this rule for union, because sometimes you're not given all the values, you're just told the probability of each. The probability using the formula, it's the probability of A plus the probability of B minus their intersection. Probability of A is 4 out of the 6. The probability of B is 3 out of the 6. And their intersection, subtracting it, is 2 out of 6. 4 plus 3 minus 2 is 5, 6. So either way, you're going to get the same answer. Any questions on finding the probabilities? A Venn diagram is used a lot in these cases. So the whole outside is the whole sample space. A will have 1, 2, 3, and 4 in it. B will have 2, 4, and 6. So we know they overlap. The two they overlap at or intersect, those would be in the overlapping circle. So A is 1, 2, 3, 4. B is 2, 4, 6. And rolling a die is 1 through 6, 1, 2, 3, 4. The only one missing is the 5. So 5 would be outside. Then you can see that this is where they intersect. All of this would be the union. This is the only one not included in the two together. It's just another way of looking at your set. Any questions? Let's draw the Venn diagram for this one. Well, this one, they have nothing in common. So if you do overlap them, there would be nothing written in this spot. Because A is 1, 3, and 5. And B is 2, 4, 6. Which takes up all of our numbers. So unlike this one having a 5 out here, they are all included in here. But this doesn't have any overlap. So sometimes instead of showing an overlap, you just write 2 separate circles. Because there's no intersection. Neither one is wrong. But if you see them written separate, it's just because they do not have an intersection. It's the null set, the empty set. Any questions on that? So go ahead and draw the Venn diagram for this one. So A has 1, 2, and 5. B has 2 and 5. So notice 2 and 5 is where they overlap. But A also has 1 where B doesn't. And there's nothing B has that A doesn't. 1, 2, so we're missing 3, 4, and 6. So they would be out here. Notice that all of B is inside A. Sometimes what they'll do then is put that whole circle inside it. So we have A, and then it'll go B. To show that B is all inside A. Neither one is wrong. But when you see that, that's just this case that there's nothing in B that's not in A. Any questions on that one? Try the last one. These two are both exactly the same. So you could put one circle, A and B, if you wanted. Like that. Or sometimes they'll use two different shades and show that one circle and the other circle are the same. Or if you write it this way. Like that. Any questions on the Venn diagram? Or finding probabilities on them? Games of chance can be repeated. An idea that we have already used, the coin can be flipped again and again and again. The die can be rolled several times. But if you think about pulling a card from a deck of cards, can it be redone? It depends. Because if I pull a card from a deck of 52 cards, if I don't put it back in, now I only have 51 cards. I'm changing my probability. So on some things you need to be careful. When I toss a coin and toss it again and toss it again, each time I have the same probability, the same thing with a dice. But a card, if I don't replace that card, I'm changing the probabilities. So events A and B are independent if knowing whether or not A occurred does not give new information about B. For instance, if I pull an ace of clubs out of the deck of cards and I replace it, when I shuffle and pull the next card, I still have all 52 cards. What happened the first time doesn't matter. They're independent of each other. But if I pull out an ace of clubs and don't put it back in, now I've changed my probabilities. So when you're doing one after another, you want to be careful whether they're independent or not, because that could change the next probability. The rule of multiplication, if two events A and B are independent, so if one cannot affect the other, then their probability of the intersection you can multiply together. So if we're tossing a coin twice and we want the probability that they're both heads, we could just use the probability of heads times the probability of a head. Because tossing a coin, they're independent of each other. When you toss a coin, the probability of a head, remember the outcome is head or tail. So the probability of a head is 1/2. The probability the next one is a head is 1/2, 1/4. Rolling a 6 and then rolling an even number. When you roll a die, they're independent of the next one. So you could take the probability you roll a 6 times the probability an even even, I'll just put even. And the probability of rolling a 6, and we've done these ones before last class. We just didn't put them together. We actually wrote out the sample space. So the probability of 6 is 1/6. Probability of an even is 3/6. Multiply across, 3 out of 36.
Why is even 3/6?
When we're rolling a die, there's 3 even. I don't know if I have them all written. If we looked at the entire sample space, last class when we rolled 2 die, we had this sample space, and we want roll a 6 and then an even. So this is our rolling a 6 first, this bottom row. And then the even 1, 2, 3. So it's 3 out of, there's 36 of them. So if you draw your whole sample space, that's another way of looking at it. Looking at this way, instead of looking at the whole sample, you're looking at each one individually. So the first die, when we roll a 6, there's only one of them. That's a 6 out of the 6. And we roll the next die, and even, there's 3 that are even.
Oh, okay, I get it now.
So it's showing you another way when a sample space is too large, as long as they're independent of each other, you can take each separately and multiply them together. Any questions on that? Okay, let's look at some cards. So if we want to find we're going to start with replacing it. So that means these are independent. The probability of drawing a card, replacing that card and drawing another one, that makes them independent because I have all 52 cards again. I'm not changing my probability. So let's find the probability. It's a king, then an ace. No, the deck of cards, I don't know if we've talked about them yet, but these 3 here are your face cards, 3 of each suit. So these ones are called face cards. They're also a king, a queen, and a jack. And these are the numbers 10 down to 1. This is also called an ace, but an ace is also a 1. So you have the numbers from 1 to 10. And then jack, queen, king. The ones that look like hearts are hearts. The ones that look like diamonds are diamonds. And then this is a spade and a club. There's 13 of each. Spades and clubs are black cards. Hearts and diamonds are red. So if we want a king and then an ace, we can find the probabilities separately. Because they're independent of each other. And there's 52 cards in a standard deck, which means I'm not including the jokers. So the probability of a king, 1, 2, 3, 4. These 4 on the end are the kings. 4, 50 seconds, because there's 52 cards. So the probability of pulling a king out of a deck is 450 seconds. Times the probability of an ace. Well, that king that I pulled, I put it back. So it's 4 out of the 52 because there's 4 aces. 16 multiplying across. 52 times 52 is 2704. If you wanted the fraction, the decimal, you just divide those. Or multiply by 100. It's not even a whole percent. A 0.5% chance that if you draw 2 cards, the first would be a king, putting it back. The next one an ace. Highly unlikely. So don't bet money on it. Any questions on that? Okay, find the probability that we would draw a heart, put it back, and then draw a red card. So probability of a heart, there's 13 out of the 52. And you don't need to reduce these, but heart is 1 out of the 4 suits, it's 1/4. So that would work also. Red is half the cards, so you could use 1/2. Or 26 out of the 52. Any questions on those? Positive.
So with this one, do you have to put it in percent? Does it?
No, you don't have to. I was just showing you what it would
Okay.
be, but we could. 338 divided by 2704 would get us the decimal. And then multiply by 100, 12.5%. On a test, if I don't say which way to write it, then it would be up to you. I know there'll probably be at least one problem where I will say write the fraction, decimal, and percent, so that I know you know how to go back and forth. So that's why I like to practice with all three. Any questions on that? Okay. What if instead we're finding the probability, draw a card without replacing it, draw another card. They are not independent of each other, because now there's only 51 cards left in there. You can still, if you're careful, use the same probabilities. You just have to know what card was pulled out and then make sure you don't use it when you're finding the second probability. So if we did the probability of a king, then we'll see how it changes. I think we did a king and an ace. Yeah. So this time we're not replacing it. When we start out, we have all of these cards. The probability of the king, there's 4 out of the 52. 1, 2, 3, 4. Now, assuming we pulled a king, so one of these, I don't know which one, but one of them is gone. The probability of an ace, now I only have 51 cards, but I still have an ace. All 4 of them, because I pulled out one of these kings. So I have 4 out of 51. So you can still do the same probability, you just have to remember that one of the cards is missing. Any questions on that? What's the other one? Heart and a red card. Go ahead and do the next one. We pull out a heart, we don't put that heart back, and then we want to pull a red card. What's the probability? So the probability of the heart, there's 13 out of 52. Now I don't know which heart is missing, but one of them is, and I didn't put it back. So when I go to pull the next one and I want a red card, instead of 26, I only have 25. And there's only 51 cards. Any questions on that? Any questions? So let's see, 325 divided by 2652. This one I got 12.3%. And still not a whole percent. But any questions? Do you need to do more, or are you comfortable with the cards?
I think I pretty much understand it.
Yeah, it's not too bad. The biggest thing is knowing a deck of cards. Students don't play with cards like we did when I was younger. Oh no, we played cards every weekend. A little different now. Any questions? So you could have a picture of a deck of cards during the test up, maybe open it ahead of time, or print a copy so you have it there. When I teach this in class, I have these printed on index cards so that everyone has one. Any questions? Law of large numbers, and we'll get a definition in a minute, but as we mentioned previously, there are some random processes that is difficult to imagine repeating. If you think about, there's a 40% chance of rain tomorrow, but once tomorrow has arrived, we can't go back and repeat the process and see if it's different. So some things you can't just keep repeating. Maybe you could go back over your weather map and see if something's changed each hour to see if this changes. But to repeat the same thing, it's not so easy with the weather. However, some samples can be repeated. Like the die, we can roll the dice over and over and over again. Tossing the coin. We're gathering samples. In science, the same thing, and we talked about the water in the lake. When you take just one sample, you don't know where you grabbed that from, and so you need to take several samples from all over, because there could be areas of pockets where it just sits. There could be other areas where the water flows really quickly and it gets rid of it quicker. And so you need to take a bunch of different samples and then compare them, take an average of them, somehow measure them. So science is another way where we can keep repeating something just to make sure. Imagine we have a random process that is repeated in this way, like measuring the arsenic. A trial, each individual instance of the random process. So each vial that has the water in it, each one of those is a trial. And then you get a large number of them. Each one is independent of the other. And that's your data set. And we talked about data set before. It's just all the possibilities, rolling a die 1 through 6. So your data set is all the values you gathered. I guess a data set with a die would be each time you roll it, keeping track of what you rolled. Each one is independent of the other. But that same process can be used in testing the water, testing our air. How much CO2 is there? The relative frequency of an event is a given set of trials is the number of times an outcome in an event E happens. So it's how many times it came out, divided by the total number of trials. Relative frequency, the number of trials divided by the total. That would be the percent. So frequency is how many times it's there. Relative frequency is making it a decimal. So relative frequency is the decimal or the percent, where frequency is how many times it occurred. Here's an example. Suppose that our random process is the toss of a fair coin, and that we are interested in how often it's heads. Then our sample space is heads or tails. Let's define an event. When tossing a coin, what is the probability of a heads? Well, the probability of heads is 1/2. If we toss 10 coins, how many should be heads? Well, if we toss 10 coins, half of them.
5.
More than likely, there will be 5. You could pull a penny from your pocket and start flipping it and see if you come up with 5. But that was not always the case. Usually it will be half of them, but not necessarily. And the law of large numbers says the more you do it, the more likely you are to eventually get half of them. Now there's you could go to this website, which I'll open up. Oops. It's www.random.org. Okay, it didn't type. Okay, there we go. Now, it doesn't always open to this page. Usually you have to hit a few things before it goes to that page. I spelled it wrong. Yeah. So notice right here, it says games. We want the coin flipper. You can pick, well, we're going to flip 2 coins. Well, no, we said 10 to start with, huh? 10. And then you can pick different coins. I'm trying to remember. I think these ones were kind of small. I don't want them too big because, well, you'll see. But what this will do is flip the coin. So if we flip 10 coins, we said 5 of them should be heads. Let's see, we got 1, 2, 3. 3 of them were heads. But the more you do it, the more likely that you'll get it. So if we flipped again, 1, 2, 3, 4, 5, 6, 7, 8 heads. So each time you do it, it's not necessarily gonna be 50% or half of them. But in the long run, it would be. So if we do this 100 times and find the average, eventually it should, notice this one is 1, 2, 3, 4, 5 heads. We can go back. Yeah. Instead of 10, try 20. If we flip 20 coins, how many of them should be heads? Anyone?
10?
Half of them, because the probability of getting heads is 1/2. So half of them. 1, 2, 3, 4, 5, 6. We only got 6. We try it one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9. Almost. Oh wait, gotta go more. 10, 11. So 11. That was pretty close. Any questions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. So we're getting pretty close. Any questions on that? Now the probability. I think it's 13. Now let's look. It's not Super Bowl. They have a lot of stats on it now. 14. So it was Kansas City had the most for 14, but Philadelphia tied them. Did I put it in a row? Yeah, 14 is the record. It used to be 13. Now, each time they go out for a coin toss, it's still a 50-50 chance they're going to win the coin toss. So each time there's a 1/2 chance or a 50% chance to win the coin toss. Each time, 1/2, 1/2. One half times 1/2, 14 times is the probability of winning 14 coin tosses in a row. That's the same as 1/2 to the 14th. Because you're multiplying the same number times itself 14 times. So you could take 1/2 times 1/2 times 1/2, 14 of them, or you can take 1/2 to the 14th power. Notice 3.7, but that's to the -9. This E means a 10. So it would be 3.7 times 10 to the -9. 4.1, 2, 3, 4, 5, 6, 7, 8. If we make it a percent, multiplying by 100, It's very unlikely. So after the first team had hit, I think it was 10 times, the people were betting more on if they would win the next coin toss than the game. Because the odds were so unlikely, or the probability was so unlikely, that people were making bets on it. And it was still a 50-50 chance that you would win your bet, because each time they toss, it's a 50% chance they will get it right. But to have that many right in a row, 14 of them, is really small. Any questions on that? I thought it's kind of interesting that. And if you like football, it's a good one. What time is it? Law of large numbers. Imagine a random process such as a game of chance that can be repeated independently many times, and we've talked about those. Let E be an event associated with a random process, and suppose P of E equals P. Then the relative frequency after sufficiently many trials is almost certain to approach it. And so we said the probability of heads should be half of them. And we were getting pretty close. We got a, what was it, 11 out of 20, which is almost half. But the more you do it, the closer and closer you will approach this. The law of large numbers does not say that the relative frequency is unusually large in the first 100 or so trials. Then it will be unusually small in the next 100 or so. It just claims that it will balance out somewhere along the way if you do it enough times. One example, how many African elephants are alive in the wild today? This is not a population that one can count directly. Ecologists must use various sampling methods to estimate it. Consider two possible ways of expressing the results of one of each sample. There are 511,752 African elephants alive in the wild today. This makes a measurement claim with inappropriate precision. There's no way they counted all of them. Maybe they would say there's approximately 500,000 African elephants, but to get that precise, there's no way they can count all of them. The next one says there's a 95% probability that the number of African elephants alive in the wild today is between 450 and 650,000. That's more appropriate, because viewing how many are in each area, then we can come up with an estimate, and then maybe you do a few of them so that you know with 95% confidence that it's between those two values. Remember when we did the standard deviation and we took plus or minus that amount? That's what they're doing here. This is an example of how probability language can be used in specifying precision. It gives a range of values together with a level of assurance that we can claim. So if it was even less, like they only looked at one area, but then they're putting it onto the rest, maybe it's an 80% probability that it's between those two. But to get an exact value, there's no way that you counted every single one. And so they use a range of values. Is there any questions? Okay, so that is everything from 5.2. Try the homework problems. I think most of them came from this section. Or the section before. But try the homework problems, and then if you have questions, we'll go over those on Friday at the beginning. And we'll start 5.3. Any questions?
No.
Okay.
No,
All right, have a nice day.
Thank
thank you,
you
you too.